And chapter 5 is all about polynomials, and we've already kind of started talking about polynomials when we started off in the previous chapter about quadratics, which is just like a more specific type of polynomial. So the topics we're going to talk about here to finish the year out is adding and subtracting, which we've already kind of talked about, multiplication and division, synthetic substitution, factoring, and solving. And both these factoring and solving topics we're just going to do a little section of. This is actually a very rich, big topic. We'll cover most of that in second semester, but we'll start looking at some of these factoring and solving techniques that are pretty similar in chapter 4 on quadratics. So we'll start some of those ideas and techniques here, and we'll continue those two topics in much greater detail second semester. So this is that's the list of topics that we're going to kind of talk about to kind of finish up the year, or the semester, I should say. Okay. So let's jump in here. So let's say we have two polynomials. Here, f and g. Actually, let's write that right example. So if I want to talk about the addition of these two polynomials, if I want to know the function f plus g of x, one of the really nice things about polynomials is to figure out that sum, we can just add the two individual polynomials. That's pretty dope, because that's easy to do. So we do this, and now I wrote the two parentheses here. But because the symbol in between these two parentheses is just addition, there's really no reason that we need those parentheses there. So we can drop all of those, and it really just becomes combining like terms. So those guys could combine, and these guys can combine, and these guys can combine, and this guy just stays the same because there's nothing to combine with. Reminder, when we're adding monomials, we add the coefficients together, but the exponent stays the same. And that's all there is to it, right? Pretty easy. We did this a little bit at the beginning of chapter 4 also. Any questions on this one? Okay. Works very much the same way. Again, we can just subtract the two individual polynomials. But here, the parentheses definitely matter because we have to make sure that we distribute the negative across that other polynomial. We can drop the parentheses in the first polynomial because there's no symbol in front of it. There's no negative sign or anything. Well, we'll distribute that negative, and then we'll just combine like terms again. So the x cubes can go together, the x squareds can go together, the constants go together, and then the linear term just stays the same because it doesn't have a like term to pair with. And again, we're just adding the coefficients, but the exponent stays the same. So there's that. Any questions on that one? Again, pretty straightforward, right? Nothing surprising here. Multiplication. So again, same idea. The product of the two polynomials we can find by just multiplying our two polynomials together. Now, one way we could do this multiplication is just multiply each term in the first polynomial to each term in the second polynomial. Like this, but that's kind of a lot of stuff to keep track of, right? We have 12 little multiplications to do there. We got to make sure we do all of them. We got to make sure we do them correctly, and then we got to sift through all of that stuff to get the like terms to combine together. I'm going to present you another option that we can do instead that's maybe a little bit easier to kind of keep track of everything. Not that this is a difficult problem to do, but in terms of keeping track of everything, sometimes things can be a little bit difficult. So I'm going to write one polynomial horizontally, and I'm going to write the other polynomial vertically. And you'll notice when I did this, I included this 0x term. Why did I do that? Well, you'll notice that in that first polynomial, I have no x term. And things work out a little bit neater if I include a spot for every term. So even if I don't have that term, I can just put in like a 0x or whatever in there. And then I'll make myself a little grid, kind of like that. So each box in this grid represents a multiplication problem. So in this first box, we're multiplying 3x cubed and 5x squared. Reminder, when we multiply two monomials together, we multiply their coefficients. So 3 times 5 is 15. And then we add the exponents. So 3 plus 3 is x to the 6th. And then I'm just going to continue doing this for each box in my grid. So 18x to the 5th, negative 21x to the 4th, 24x to the 3rd, and so on. I'm going to stop talking as I'm writing these down, because if you're doing the same thing and I'm saying a number while you're writing a number and they're different numbers, that can get terribly confusing. I think that was one of the plot points in Home Alone as to why Kevin got left behind, where somebody was messing with the somebody when they were doing the head count on the children. I think that movie's been on a lot lately with the holiday coming up. So again, each one of those little multiplication problems was easy to do, right? They're all little monomial multiplications. They're all pretty easy. Let's just take a moment and point out some patterns going on inside this table. So you'll notice that if you look at the exponents of the variables, and we look down the table, say in column 1, we go from x to the 6th to x to the 5th, x to the 4th, x to the 3rd. So going down each column, the exponent should decrease by 1. Additionally, if we go from left to right across our table, the exponents go 6, 5, 4, 3 in column or in row 1. The same thing should happen as we go from left to right across our table. The exponents should all decrease by 1. That's the advantage of putting the 0 in there. But here's the big advantage here, is that if we look on the diagonal, we have all of our like terms together. So we don't even have to do a lot of picking through this table to figure out the like terms to add together. They're all lined up for us anyways. So I have just 15x to the 6th, 20x to the 5th, and 18x to the 5th is 35th. 0, 24, and negative 21 is 3x to the 4th. Negative 15, negative 28, and positive 24 is negative 19 x to the 3rd, negative 18, 0, and negative or positive 32 is positive 14 x squared, 21 and 0 is 21, and negative 24 is just negative 24. So there's my product of those two polynomials. And this took up a little bit of space or whatever, but it wasn't very difficult to do. It wasn't that terribly time consuming versus, multiplying it all out horizontally or whatever. It takes up a little bit more space on a sheet of paper, but boy, it's hard to screw that up, right? Since all the multiplications are very easy, and then the combining of like terms should be easy because everything should line up for us. That's a pretty good deal. Okay. Questions on multiplications? Okay. Next up is division. But before we do polynomial division, I want to go back and revisit long division that we did in elementary or middle school. Yep, that long division. So let's say we have 5,823 divided by 21. This would be a problem that you might have something similar to this in elementary or middle school. So we set up, we put the divisor, that's the second number, outside of our division bar, and the dividend, that's the first number, underneath the division bar. And then we just go down digit by digit, starting on the left, and we say, okay, how many times does 21 go into 5? Well, none. So we move on to the next digit. We say, okay, how many times does 21 go into 58? That's 2. So 2 times 21 is 42. And then we subtract down. And then we ask ourselves, okay, how many times does 21 go into 162? Well, that's 7. So 147, 21 times 7. And we subtract down. And then we ask ourselves, how many times does 21 go into 153? And the answer there is, again, 7. So 7 times 21 is 147, and we subtract down, and we get 6. So we'd say that the answer is 277, remainder 6, or often we write it as plus the remainder over the divisor. So this first number, the 277, is the quotient. The 6 is the remainder. And the 21, again, is just our divisor. Right, so we remember this long division process from before. Maybe you didn't format your answer exactly the same way I did there with the fraction at the end instead of the remainder, but like, it's not hard to see what I'm doing there. It just remain plus remainder over divisor. Right, it's 277 and then 6 21sts, right? It's just basically a mixed number. So polynomial division is going to work very similarly. So let's say we have 2x cubed plus 7x squared minus 5x plus 2 divided by x plus 2. So we'll start the same way. We'll draw our division bar and put our divisor on the outside and our dividend underneath. Now, one way that polynomial division is a little bit different than long division is that we only care about the leading terms. So this first question, I'm just going to ask, how many times does x go into 2x cubed? Well, I know 2x squared times x gives me 2x cubed. So I will go then and multiply that 2x squared to the entire divisor. That gives me 2x cubed plus 4x squared. And then I'll subtract down. Now, a suggestion for you guys, one of the most common mistakes I see students make is forgetting to distribute that negative sign when they're doing the subtraction. So let's do that right now. So I'm going to distribute that negative sign, giving me a negative 2x cubed and a negative 4x squared. And then I'm just going to think about adding down. So 2x cubed plus a negative 2x cubed is 0. 7x squared plus a negative 4x squared is 3x squared. And then I'll go ahead and bring the next term down.
Wait, how'd you get the 2x cubed squared again?
It's how many times x goes into 2x cubed.
Oh, okay, thank you.
Mm-hmm. So we'll repeat the process now. So I'm going to ask, how many times does x go into 3x squared? Well, 3x times x gives me 3x squared. So I'll then take that and multiply it to each term in my divisor. It's going to give me 3x squared plus 6x, and we'll subtract down. Now I've got to make sure I distribute that negative through, so I really am going to have negative 3x squared and negative 6x. So 3x squared plus a negative 3x squared is 0. Negative 5x plus a negative 6x is negative 11x. I'll bring down the 2. And then I'll ask myself, how many times does x go into negative 11x? Well, that's negative 11 times. So I multiply negative 11 to both parts of my divisor. So negative 11x minus 22, and subtract down. So again, before we start doing our subtraction, we'll distribute our negative. So negative of a negative 11 becomes positive, and negative of a negative 22 becomes positive. So negative 11 plus 11, or negative 11x plus 11x is 0. And 2 plus 22 is 24. So my remainder is 24. So the way I'll write my final answer then is 2x squared plus 3x minus 11 plus my remainder 24 over my divisor x plus 2. Just as an aside, I knew I was done when I got to 24 because there's no variable left, right? If the degree of the leading term of the divisor is greater than the degree of what I have left, I know I'm finished. So let's do another of those. I mean, that's not a trivial process. It's rather involved. And while it's based on something we're relatively familiar with, it's complicated enough that probably deserves a second look at something, right? Okay, so let's say we want to do 4x to the fourth minus 7x cubed plus 5x minus 3 divided by x squared plus 2x minus 1. We'll set this up the exact same way. But you'll notice something. I included a 0x squared term. Why did I do that? Because my divisor was missing x squareds. This is going to make life considerably easier for you if you remember to put these zeros in for these missing terms. If we remember to put these zeros in, all of our terms are going to line up for subtraction, and it'll make life much, much easier if you considering, or than if you had forgotten to do that. Everything lines up very nice and neatly. So please make sure you do that. Any term that's missing, either in the divisor or the dividend, or both, you need to put zeros in. Okay? No matter how many terms there are, no matter where they're at, please remember to put the zeros in. Okay. So I'm going to start and I'm going to say, okay, how many times does x squared go into 4x squared, or 4x to the fourth? Well, 4x squared times x squared gives us 4x to the fourth. And then we'll multiply that to each piece. And then subtract out. So we'll distribute our negative through. So positive becomes negative, positive becomes negative, negative becomes positive. So 4x to the fourth minus 4x to the fourth is 0. Negative 7x to the third minus 4x to the third is negative 11x to the third. And 0x squared plus 4x squared is 4x squared. And we'll bring the next term down. and repeat. So we'll say how many times does x squared go into negative 11x cubed? Well, I know negative 11x times x squared gives me negative 11x cubed. So I'll multiply that to the divisor. This means negative 11x cubed minus 22x squared plus 11x. And then we have to subtract down. And usually it's easier to distribute the negative here. So let's, negative of a negative becomes positive. Negative of negative becomes positive. And negative of a positive becomes negative. So negative of...
Mr. Kulik?
Yeah.
When you wrote the second polynomial, like 4x, well, it'd be negative 4x to the fourth minus 4x cubed plus 4x squared. Why is it negative 4x cubed? Because if you're multiplying that would be multiplying the 4x cubed times 2x, right?
Oh, shoot, should be 8.
Would it be 8x cubed?
Yup. Yup. Thank you. So that should be a 15, huh? Okay. That's better. My apologies. Thank you, Mia. So we add those things down and then bring down my last term. And we'll ask ourselves, okay, how many times does x squared go into 30x squared? And the answer there would be 30, right? Because 30 times x squared is 30x squared. Multiply that.
Wait, Mr. Kulik, wouldn't that be like 34x squared because of the 4?
Yup. Sorry. Bad day for arithmetic here at the Kulik house. Okay. And then we distribute our negative, 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 positive. And we add down. So that's my remainder. Notice that my remainder can have variables in it because the degree of the remainder is less than the degree of the divisor. The divisor's degree is 2. The remainder's degree is 1. That's okay. To have x's in, we just need the degrees to be less. And there's my solution. Okay. The last thing I want to talk about today is synthetic substitution. But before I do that, we just need to talk about regular substitution. So let's say we wanted to do, we have the polynomial f of x equals negative 3x cubed plus 7x squared minus 5x plus 1. And we want to do f of negative 2. Well, all that means is that we're going to be plugging negative 2 in for the x's. So that's going to give us 24 plus 8 plus 10 plus 1. So that would be 63. So synthetic substitution is a process that will accomplish the same thing. Just a different way of doing this. So the way we set up the synthetic substitution is we start by making this like little L bracket here. And then whatever number we're going to be substituting in, we write here on the outside. And then the numbers or the coefficients on our polynomial, we're going to write on the inside of the L bracket. So this is the setup for the problem. This is the starting point. The first step is that we're going to just take the first number inside the bracket and bring it down. Then we're going to take the number on the outside, multiply it to the number underneath, write our answer here, and then add down. And we're going to repeat that until we've kind of filled up all the spots in our bracket. So negative 2 times 13 is negative 26. We add those, we have negative 31. And then negative is positive 62. And we add the 1, that's the 63. And at this point, you should say, great googly moogly, why would I ever want to do this convoluted thing when I could just do what we did before? It's so simple and straightforward. And the answer is, for substitution, you probably wouldn't want to do this. But we can adapt this procedure to do things later that it'll be really useful for, that makes life much, 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 much faster. In fact, there's a way to do polynomial division using this technique that makes life considerably easier. We'll talk about that tomorrow. Okay. So that kind of does it for today. Does anybody have any final questions?
Can we do another of the division ones? Because I don't know about anybody else, but like I'm just kind of confused on how like you're doing it.
Sure. Okay, so we set it up just like long division.